Okay, we are in section 30.3, Lenz's Law. Let's share the uh, PowerPoint, and there it is. And we start off with Faraday's Law. The induced EMF is equal to minus ddt of the magnetic flux. And Lenz's Law says that the induced current in a loop is in the direction that creates a magnetic field that opposes the change in magnetic flux through the area enclosed by the loop. Let's read that again. The induced current in a loop is in the direction that creates a magnetic field that opposes the change in magnetic flux through the area enclosed by the loop. What does that mean? Let's give you an example. I've got just a loop here, and we're going to pretend this is my magnet. It's a nice little arrow, so north is usually the point, and we use the tail end as south. So I've got a loop here. I'm going to insert a magnet. So as I insert the magnetic field is growing. The magnetic flux is increasing. It's a changing magnetic field, increasing magnetic field. Lenz's law says that as the magnetic field is increasing, the current in the loop is such that it wants to oppose the magnetic field. So the magnetic field is growing in this direction. It wants to oppose the magnetic field, oppose the growing magnetic field. So you can see that the current would be induced in this direction. The magnetic field is growing in this direction. The Lenz's law says it wants to oppose the growing magnetic field, so that would put it, from the right-hand rule, that would put it in this direction. Okay, now we have our magnet in here, and we're going to pull it out. So as we pull it out, it's a collapsing magnetic field. As the magnetic field collapses, the current is induced such that it wants to reinforce the collapsing magnetic field. So the magnetic field is collapsing in this direction. It's going to want to reinforce that. So from the right-hand rule, we can see that it's going to try to reinforce that magnetic field, and it's going to go in this direction. Okay, so growing magnetic field opposes it, goes in this direction. Collapsing magnetic field like this, it wants to reinforce it, so it goes in that direction. So that's what it's trying to say. Let's go back to the share. We'll read it once again. Now that you've had that little visual, the induced current in a loop is in the direction that creates a magnetic field that opposes the change in magnetic flux through the area enclosed by the loop. So it depends on whether the magnetic field is growing or collapsing. Let's do another little visual here. As the conducting bar slides to the right, the magnetic flux due to the external magnetic field into the page through the area enclosed by the loop increases in time. So it's increasing going into the page. It's increasing going into the page. So the current is going to be induced such that it wants to oppose the growing magnetic field. So it's going to be coming out of the page. So if it's coming out of the page like this, the current is going to be downward. If you use your right-hand rule, the current is going to be downward. Okay, now let's reverse the situation. Now we've got this bar moving in this direction, and the magnetic field is growing smaller because we're looking at a smaller area of it. So it's a collapsing magnetic field. So it wants to reinforce that collapsing magnetic field, the decreasing magnetic field. So it wants to put it into the same direction as the magnetic field that's collapsing. So it's going to be into the page, and if you use your right-hand rule, you'll see that the current is up. All right, now let's look at a quick quiz. The figure shows a circular loop of wire falling toward a wire carrying a current to the left. What is the direction of the induced current in the loop of wire? Okay, we got clockwise, counterclockwise, zero, or impossible to determine. Well, we know it's not impossible to determine. We can figure this out. So first of all, we've got, now this is not a magnet, this is a wire. We've got the current going in this direction, right-hand rule. The current is going into the page as you're viewing it. It's going into the screen. So the magnetic field is in that direction. As the loop falls, it's getting into an increasing magnetic field. The magnetic field is stronger right around the wire. So as it falls, it's going into an area of stronger magnetic field. So the magnetic field is increasing. The magnetic field is increasing, so it wants to oppose the increasing magnetic field. Let's see, the magnetic field is going this way. It's increasing. It wants to oppose it. It wants to oppose it, so it's gonna be coming out of the ring, and so the current will be in this direction. It's going to be counterclockwise. And whoops, and there it is. It's counterclockwise, and that's correct. And that ends our Lenz's law, and we'll get into the next section, which is the general form of Faraday's law. General form of Faraday's law. Okay, let's stop it here.